Hey guys, ready to do section 6-8. So go ahead and get your notes out, and we will also use Desmos just a little bit, so you could go ahead and pull up Desmos. Alright, let's get going. Enough jamming. Okay, we can jam a little bit later. Alright, so introducing inverse relationships. Okay, so we're used to seeing inverse before, like the inverse of A is like the opposite, negative A. Or it can be like a flip, like if we're doing a flip version, A, when you flip it, is 1 over A. So there's some ideas. It's like the opposite. Okay, that's usually what should pop in your head when you see that word inverse. Something's going to be switched around. Okay, so our notation is going to look like this. The inverse of a relation is like a function, kind of like this. Look down here. We did these before a couple of units ago, but it'll be indicated if we want the inverse. It'll have an exponent of a negative 1. Okay. To find the inverse of the relation, it's going to be a really simple process. All you have to do is switch, kind of like, oh, wow, okay, switch is what that's supposed to say. Switch the, okay, I'm having some kind of issue here. Let's just type this in, a text box. Yeah. Oh, I'm having issues. Okay. Oh my gosh, you wouldn't think that'd be that difficult, but my computer is, well, it's kind of slow, I think, because it's uploading the other video. Alright, all we do is switch the x and y values. So in this case, we just switch the x and y values. Oh my gosh, that's so hard. Not. Okay, when it's a one-to-one relationship, a function where the original and its inverse are functions. This is how you tell if it's one-to-one. It is a one-to-one function if the original and its inverse are functions. Okay, we will practice that in a little bit if it's a one-to-one relationship. So remember, for function, we did vertical line test. That's how we did that a couple units ago in Unit 2, where you did the test of the vertical line, see if it crossed the graph. If the graph intersected any vertical line more than once, it was not a function. So that's what's going to make a one-to-one relationship if the original and its inverse are both functions. They pass the vertical line test. All right, let's see if my pen works now. So, R. Alright, so the inverse of R. All we're going to do is, like I said a second ago, switch the x and y's. So we're going to change this to -2, 1, and then a comma. So all I did is switch these two, their places, 4, 2, -1, 3, and -2, 4. Alright, so this is the original, and this is its inverse. Okay, so we have to test each to see if it's a function. Now remember this, you did that card sort thing, where I'm going to kind of show you this visual, because this visual will help you. Remember I said that it will not be a function if you have two of the same x's. In other words, if there's something coming from a number twice. In this visual right here, we don't have that. So this one will be a function, okay? So the same thing, remember we don't want x's repeated. So is R a function? And what you want to look for is repeating x's. Look for repeating x's And then that will be a result in not a function. All right, so and we're doing each one separately. So just the R set. Do we have any repeating x's? 1, 2, 3, 4. No, they're all different. So since they're all different, we're good. We passed the vertical line test. So yes, R is a function. What about this one? So we look and see now. So we have, remember, new sets of x's. So negative 2, negative 4, or positive 4, negative 2, 4, negative 1, and negative 2. Does anything repeat as far as the x's? Again, you're only checking the x's. Yes, negative 2 pairs with 4, negative 2 pairs with 1. So in other words, those two dots would be above each other. One would be above the other one on your graph. If they're both at negative 2, 1, and negative 2, 4, they're going to be above each other. So that would indicate no, that it would not pass the vertical line test. So it is not a function. Therefore, is it one-to-one? The definition of one-to-one up here is that a function where the original are both functions. Are they both functions? No, we would need both of them to be yes in order to answer that as a yes. Okay. Alrighty. So this is the thing, and I'll just highlight this real quick. This is what messed us up on number 2. The two negative 2's being in the x spot. You can't have that to be a function. Okay? Alright. Number 2. I'll leave that one for you to try. Okay? Since that should be pretty easy. Now on one like this one, next one, I'm just going to remind you of this. These are really coordinates. What coordinates are they? 0, 6. So I'm going to write this out in set notation. Well, actually, that's for the inverse. Sorry about that. But if we could write them out here, I guess. 0, 6. Then we have a 1 and a 2. And then we have an 11 and a 6. Notice how there's no arrows coming from the 8. Oh, I don't know why my thing wants to mess up like this. 11, 6. It's like extra slow for some reason. So there's nothing going from the 8 to the negative 5, so we don't include that because I don't have actual mappings. These are mappings pairing up numbers, but no arrow means I can't just make it up. So now we do the inverse of each of those, which would be 6, 0, 2, 1, and 6, 11. Alright, now using those values, go ahead and answer these. I think you can probably do these on your own. Alright, pause the video, try them real quick, shouldn't take you very long. Press play when you're ready to see the answers. Hey! Alright, here are your answers. Number 2. We have a matching set of x's for the original, so that would fail the vertical line test. And then here's your inverse. So therefore the first one is not a function. The inverse is a function, making neither there. So this is not, my original is not a one-to-one function because one of these are not a function. Number 3, the original is a function. And then the inverse is not a function because we end up with the 6 in the x spot and then another 6 in the x spot. We can't have two of the same x's. So yes, no, making it not one-to-one. Okay, and there's an announcement. Alright, so let's review a couple things. So horizontal line test. Yeah, we have a vertical line test, but now we have a horizontal line test. The vertical line test is used to determine whether a relation is a function or not. Okay. The horizontal line test will be used to determine whether the inverse is a function or not. And of course we're going to have to graph that to see what that looks like, but you just would do the same thing. So both, except we test a horizontal line across the function instead of a vertical line. Both the relation and its inverse must be a function in order for it to be one-to-one, which is the same as before. Alright, let's look at a couple examples. Determine whether a relation shown represents a one-to-one function. So, in other words, we're going to test the vertical line, and we're going to test the horizontal line. Horizontal, that's what it says. My pen is a challenge today. Alright, let's see if I got any. Nah. Alright, so now I'm going to take my imaginary pencil, so I'm going to drag from, so for vertical, left to right. As I drag my vertical line across that graph, do I intersect? Or you can do this, you can just imagine. I'm drawing tons of vertical lines. Do I pass the vertical line test or not? Yeah. I intersect only once on my line, and I'm looking at this bold line right here. Don't get confused with the X and Y axis. Yeah, I'm only intersecting each one once, so it does pass the vertical line test, definitely. Alright, now we're going to test the horizontal. So in this time, I am doing horizontal lines. So do I cross? Oh my goodness. I was trying to get another color, people. Come on. Alright. Am I intersecting my line only one place at a time? Yeah. As I'm going through, same thing. I'm intersecting here, and here, and here on my horizontals. It's working out the same way. So yes, it passes the horizontal test. So answer to this one would be yes, it is one-to-one. It is a one-to-one function. Okay, let's test number 2. So first, the vertical line test. You can just imagine sketching a bunch of vertical lines. Do I intersect more than once at a time? No, so it's good on that. Okay, horizontal. Oh, I get to the graph down here. Whoa. I'm intersecting horizontally multiple times, so we can tell this is not going to work out. Yeah, the horizontal line test fails. Therefore, no, it is not one-to-one. Okay? Alright, there's an example of your horizontal line test. Right. Next page. So, with our inverse functions, if we write it as the notation f of x, all we have to do is use that little -1 sign, but it's going to be like this between the parentheses and the f. So it looks like this, f of -1, it means the same thing. And then we're going to practice solving these. So how do we solve the inverse? When it says find the inverse of each function. Okay, this is the type of problem you have to know how to do. And here are your steps to be able to do that. It might be a good idea to highlight these. Oh, so how do we get the equation? So we got a pretty quick way to get the equation of the inverse. The inverse of this, which is y equals 5x. How do we get it? Okay, so we're going to do these steps. First, we replace the f of x with the y. It just makes everything a little bit simpler because we're going to have to rearrange stuff. Alright, that's step 1. Replace f of x with y. Next, we interchange x with y. So, in other words, we just literally physically switch them wherever they are. So, we're going to switch them and end up with this. X equals 5 times y. Now, what do you think we're going to do? Yeah, we want to get y by itself. And that makes sense, since in the previous examples, we physically switched the x and the y to get these, right? That's all we did, was switch the x and the y, so it's going to be the same way. So to get my equation, I'm going to now do this step and solve for y, so divide by 5. And y is equal to x divided by 5, or that's the same thing as 1/5 x. So I have a 1 up there. And then you can rewrite it as an f of -1. So that is our answer. Okay? Alright. Hopefully that seems easy enough. Alright, let's do one more together just to verify. That one looks kind of easy. Let's do one like number 8. Okay, so first step is replace this with the y. Okay, next step is swap the x and y. And then now we want to isolate y. When you have it like this, this is a grouping within a grouping, and you got to get rid of this first. So the opposite. What's the opposite of divide by 3? Times both sides by 3 to cancel that out. And then we would have 3x is equal to y minus 8. And last but not least, we would add 8. So f of negative 1 of x is equal to 3x plus 8. And there's your inverse. Okay? Alright, we've got some with some square roots down here. Let's go ahead and look at these. We'll do this one. Alright, so replace this with y. Switch it around. Pretty easy process, right? But you don't do this too often, so the hard part is remembering the type of problem and the different steps, okay? Inverse, inverse, switching x and y. Maybe just remember that. Alright, isolate the y. So we got to add the 9 to both sides. So x plus 9 is equal to y squared. Okay, y is not by itself yet. We have to do what to get rid of that exponent? Yeah, square root. Square root. And it's saying as long as x is equal to or greater than 0. So what they're just saying is they don't want a negative response down here. So that'll go away, and we can have f of negative, oh, I put the parentheses too early. Whoopsies. And I missed the negative 1. I'm just all over the place here. Negative 1 of x is equal to radical x plus 9. Okay? Alright. Makes sense? Hopefully. Alright, then one more thing we gotta do. So this was the case if x was greater than 0. So what number would have to be here in order to keep this value greater than or equal to 0? So we're going to add one more thing. I knew there was something weird going on here. Yeah. So we have to say that this would be, let's see, what number would make this 0? Would be negative 9, right? Negative 9 plus 9 would make this a 0. If we have a negative 10, so in your mind, substitute in negative 10. We would have, well, I'll just write it up here. How about that? Negative 10 plus 9. What the point of this is so we don't get a negative under the square root. So we're going to have to add a stipulation here to make sure we don't get a negative. So negative 10 plus 9 is negative 1, right? And then this is not allowed. So we can have a negative 9 here, and that would make this 0. Radical 0 is 0. So we have to say with stipulation that x has to be greater than or equal to negative 9. So any number greater than negative 9 is allowed here. That's just so we don't get a negative under the radical. Okay? Alright. Now with your cube root, which you're going to have to do over here, that doesn't really matter because you can have a negative under the square root. So these don't come along very often, but that can be kind of tricky if you don't see it very often. Alright, why don't you go ahead and try 7, 9, and 11. Just these 3 problems. Pause the video and press play when you are ready to see the answers. Alright, here we go. Number 7, the inverse is x plus 7. Number 9, the inverse is negative 5 halves x plus 5 halves. And number 11, the third root of x plus 6 minus 4. Okay, I'm going to show you what these look like graphically. So I'm going to graph, I've already entered these in actually for you. Number 6 was, the original was 5x, the inverse is 1/5 x. What do you think they look like on the graph compared to each other? Let's take a look. 5x and 1/5 x. So here it is, 5x and 1/5 x. I'm going to go ahead and show these, and they look like this. Okay, so kind of interesting. All right. Let me show you show you the answer to number 11. This and this. So number 11, oops, looks like this and this. Okay? I'm zoomed way out, but anyway. Wow. Okay. Very interesting. Does that make sense that that would be an inverse? Yeah, it looks like it's a reflection, right? Over, remember in geometry we had this line, x equals y line. It was this dashed diagonal line, and it goes through, oh, I can't draw on this, but anyway. It goes like this, and it was through 1, 1, 2, 2, 3, 3, and we had that diagonal line, and then we flipped stuff over it, and that was in the symmetry type lesson, doing reflections and stuff. So this is symmetrical, and you're going to notice that in any kind of graph where you graph the original and its inverse, and see the same thing happens on this one. We've got this line that would go right down the middle of both of these. So that's one thing to keep in mind as far as graphs to be able to tell. So graphically, it's easier to tell if you have inverses than if you do it, and you can do it this way, than if you do it this way. So this composition of functions way can be confusing, and I don't want to confuse you, so the least confusions we can have, the better. So the case, and this is all started on the next page. Okay, so let's do this example. So a triangle ABC, and again, the nice thing is they tied this from geometry, since you had geometry and you kind of seen inverses before, but you didn't really know what they were. Triangle ABC is formed by the points of the relation -1, 6. So I'm going to go ahead and plot this. Let me get black. -1, 6. 1, 2, 3, 4, 5, 6. So this is on the back page of this packet. Alright, then we have -7, 2. 1, 2, 3, 4, 5, 6, 7, and then 2. And then we have -5, -3. 1, 2, 3, 4, 5, -3. Okay, about like that. And so being a triangle, alright, now we can get the inverse of the relation easily by what we just did a second ago. If these are my coordinates, I would do what to them? Reverse them. Yeah, inverse, reverse. Sounds very similar, right? Inverse, reverse. Alright, 6. -1, 2, and -7, and -3, and -5. So that would be the inverse, and yes, let's go ahead and graph it. Two, -7. Alright, am I in the right area? Yeah, it looks like I am. Oh, that's not very straight. There we go. Alright, let's draw that dotted line I was just talking about. The x equals the little y line goes, oh, whoa, went a little bit off track there. Alright, so that's that line, x equals y, that these are all reflected over. This just means whatever x is, y is whatever y is, x is, and they can be switched. So that was item 1, and that was item 2. Okay, I already did that. What do you notice about the graphs? So we've already mentioned this. They flip over the x equals y line. So let's go back. If you need to pause the video, if you're not ready yet, go ahead and do that. But I'm going to go ahead and go back. So we're going to test these. We're not going to do this way. Okay, we're going to just cancel that out and determine whether these are functions based on my graph. Okay, x squared plus 8 is the first one. So let's go ahead and eliminate these. X squared plus 8. The next one being x squared plus 8 and radical of x minus 8. No, that's not right. Just trying to remember. Radical of x minus 8, resulting in this. Okay? So this, now the first one had a stipulation. So I need to go back here and notice this, that my stipulation for this one was that if x is greater than or equal to 0, in other words, if x is positive or a positive whole number. So I'm going to go back and look at that, and if my x's are positive whole numbers, that's going to be this section of the graph right here. So really I'm not including this half of the graph. So for ones like that, you have to ignore all of that. Okay? So I have this one, and then I have this one. And if I would imagine that dotted line, would these be reflected over that dotted x equals y line? And yes, it would. So this one is, and of course we want the endpoints to match as well. And we know by the problem, by doing it, and these ones that they definitely were inverses because we were coming up with an inverse. These ones we're trying to decide whether they are inverses or not. So in this case, we can say yes. Yes, they're inverses of each other because they are reflected over the x equals y line. Now, the second example is an example of one that is not going to be a inverse function. So let's type these in and see what we get. Negative 4x plus 5. And x divided by 4 minus 5. Okay. And this one, if we would start with our x equals y line, it would go like this. And that definitely is not going through. We would have to go through this point for sure. To make it look appropriate, and as you can see, our dotted line would be like 1, 1, 2, 2, 3, 5, 5, 10, 10, and that dotted line does not cut these in half symmetrically. So that would not be a symmetrical picture, I can already tell. And I guess, I wonder if you could do this. I just had an idea. Yes! That's a great idea. Okay. Woohoo, Miss Hensley! Okay. So y equals x, I can just type in that y equals x line and see, oh, that is not symmetrical over that line. And I could even change this. I could possibly change this to a different color or something. Or dotted. That's what I was trying to do. Yeah, let's make that a dotted line. There you go. So you could do this easily. Just keep changing these two equations out and then see if it's symmetrical over that dotted line and keep that dotted line there. Yeah! Woo! That just came to me. So this one is definitely a no. So composition-wise, yeah, you could do it. You also could just find the inverse of this one and see if you get that one. That's another way of doing it, but the graphing way, of course, is a nice, quick, easy way to do it. So yeah, there you go. Alright, I am not really, let's see. I'm having a senior moment. Now I'm not worried about these. We're not going to do a ton of many of these. This isn't really going to help you. The main thing would be deciding if they were inversers or not. So, alright, so that'll be it for this video. Alright, see you next time.